And we're missing 2. All right. So this is going to be Exam 2, Chapters 3 and 4. 101, 2, Chapter 3 and 4. And this is their review. On 17th, yeah. President's Day. Happy President's Day. Okay, so before we get started with this, I want to be sure everybody is ready for the lab. And your lab notebook, everybody knows what it looks like because I showed you and actually sold a few of them here. What I want to see on the lab notebook cover is your name, class, like that, the class, and actually the semester. And then class and semester will get everything else you need. That should be enough of cover, right? Then on the inside, you got a number every page. Starting with the first one that's available, it'll be right-hand facing page. So at the top right-hand corner, start off with 1. And when you flip it over, page 2 will be over there, right? And then page 3 will be like this, okay? So every right-facing page will be odd. Every left-facing page will be even. And if these notebooks, if they're consistent manufacturing, there should be 200 pages. So if you end up with more than 200, less than 200, you know you made a numbering mistake somewhere. Okay, that's the first thing. Number every page before you do anything. In ink only in these notebooks, no pencil. Okay. Then on the first page, you want table of contents. Okay? And then you just write down whatever the lab is and then the page number. Where does it start? That's all you need, because it's going to keep going until you get to the next one. And the next one is going to have a page number. So everything from here to here is allotted for your first experiment. Okay? So you only need the beginning page. Okay? And then probably want to skip 2 and 3 and start your first experiment on 4. Right? You have experiment 1, and then you have the title, and then all the information you need to do the experiment. Right? Well, this is not 1. In fact, you probably won't have 1 in there because that was Excel, wasn't it? But we haven't had it since then, have we? Let's see. This feeling we did do 1. Laboratory techniques. All right, so you won't have that one either. So waters of constitution and hydration will be simply because the first and the second one were not formal. You're just working from a sheet. So you can start with the third one, and it'll be here. And you'll put the title, you put all the information that you need to write a report. You want to put your methods in there step by step. And you also want to have a thing on why you're doing the experiment. What's the whole idea behind the experiment? Right. Background, introduction. Then a safety blurb, safety concerns. Then you do your procedure, step-by-step procedure. And always always do all this stuff on even pages, right-hand pages. Leave the odd pages alone. Oh, excuse me, that's not right. 1, 2, 3, odd pages. So you skip this one. Sorry. Right-hand facing pages. The right-hand pages are the ones that you write on. And you leave the left-hand pages, or the even pages, blank. For 2 reasons. When you're writing things in here, if you say you write your method out and something changes in the lab, you have to change something. Something happens, you need to make an observation. You've got this space over here that you can do it. And when you're writing your method, when you're writing in your lab before you go in there, you want to skip lines. Leave a space between your lines in case you have to make a small correction. Then you got space for it. You know, don't bunch them right together, because then you've got no room to go anywhere except this side. So you can make big corrections over here, like you have a massive amount here, but you don't have room below it to make the correction. If you have a massive correction, you just X through it and then reference over here and fill in the information. The other thing is, when you get to pages down the line, maybe you want to cut and paste something to put in there. Results, maybe. You generated results in Excel, print it out, cut, paste it in there, like a graph. Or you can draw the graph, since these are quadriline, you can draw the graph. But these left-hand pages are for extra information. Okay, so you never write on those. You always write on these, leave these available for later. So the whole point behind a lab notebook is a record of what you're going to do and what you actually did. Right? So before you go in the lab, you have studied the experiment enough so that you can write out what needs to be done and you've got it firmly in mind. That's your first step in safety. Know what you're going to do before you go in. And then as you complete the experiments, you've got that information there. You can take your lab notebook, you can write your report. You don't even have to look at the hard copy. Right? Once you put it in here, you can throw the hard copy away. If you've got everything in here that you need, right? If you don't, you throw the hard copy away, then you're in trouble. So that's why this needs to be complete. Then once you get all of your information in there, you can do calculations in your lab notebook. You can take that lab notebook and write your formal report. Okay. One thing I do not want to see is regurgitated methods from your formal report. Right? If you just copy your the hard copy. You just take the hard copy procedure and transcribe it into your report, that's bad. I want to know what you did, not what you're going to do. Right? The printed copy is what you're going to do. What you actually did goes in your report. That's why, if you look at I gave you guys one of these, I'm pretty sure. A rubric, right? Actually, I gave you a sample, right? Remember that one? I gave you a sample, then I gave you a blank rubric. And one of the things in the blank rubric is grammar. When you write your procedure, what you actually did Your grammar is going to be third person. Everybody know what that is? I is first person. I, me, first person. You, if I say you, I mean second person. And I say it or them or they is third person. So in a lab report, we want to say it. Third person, passive, past tense. So an example. Say you needed to weigh out 20 grams of a sample or something. And you say, 20 grams of sodium carbonate was weighed. So 20 grams, third person, was past tense, was weighed, which is actually passive past tense, was weighed on an analytical balance to 0.001 gram accuracy. Okay, that's an example of a step in your procedure in your formal report. Third person passive past tense. Notice that if grammar and wording indicate the printed procedure was copied, you get a 0 for that one. Okay. So it behooves you to pay attention to your procedure and do it this way. And that's why I gave you an example. It's a pretty good example, a sample, right? So you can see how the wording in that sample. Okay. So you've got your lab notebook set up, and that's what I'm going to look for on Wednesday. I'm just looking to see if you got all your paper pages numbered, you're identified, you got a table of contents. I won't look at your procedures until I pick up the notebooks at the very end. Then I'll pass judgment on your procedures. Now, it doesn't have to be pretty. You know, lab notebook's not necessarily pretty, so you don't write in a separate manual and then copy it into your notebook. The only thing you have at the lab bench is your lab notebook. You don't have the printed copy. Your lab notebook, that's why you need to set it up so that you can follow along with what you studied and do the experiment from your lab notebook. And as you gather data, it goes in your notebook right then. No recopying. Recopying, bad. Okay. So I'll save the discussion of writing a formal report until you actually have some data to work with. Okay. But that's how you set things up and get ready for the, of course, you're going to have a lab coat by then, right? Everybody got a lab coat? Okay. If you need goggles, we have them. They're probably scratched up, so if you don't have a pair, you may want to get a pair. We have gloves, disposable gloves, so you don't have to get those. And everything else we provide. Okay. Waters of constitution and hydration. That procedure is going to be using fire, a Bunsen burner. So you need to know what you're doing. You need to not wear loose clothes, lab coat, button, that'll keep everything in. You got long hair, do that. You know, back out of the way, right? The only reason I don't wear a tie, it's just something else to get caught, burned, shredded, whatever. Okay, so that's the lab. Any questions about the lab from here or remote? Okay.
No,
Yeah, somebody say something?
No, I don't have any questions.
on the front, you just said our name, the semester, and then the class. Is that it?
Yes, your name, class, and semester, right. That identifies that notebook as yours and nobody else's.
Okay.
You can put my name in there if you want to, that's extra. that's the bare minimum information.
Okay.
Okay, let's see. We are recording. So now we're going to get on with the review. Let's see. There we go. Okay, so the next exam is going to be on chapters 3 and 4. Chapter 3 is stoichiometry. 4 is chemical reactions and solutions to stoichiometry. So they're both on stoichiometry, actually. Anybody had a chance to look at your review document? That will guide your study. If you, after you've read the chapter, done your homework on, let's see, this was OWL, done your OWL homework. The next thing you want to do is focus on the review document. If you can work all these problems, answer all these questions, then the exam will be a piece of cake. Okay? So that's one of the reasons I created this thing. So if you're short on time and energy, then focus on that document. Right? If you're like I used to be and you wanted to know everything backwards and forwards, it didn't matter what that was. You know, and if you've got time, you just crunch through it. I'll do these two plus end of chapter problems, and you go out and look for other problems on the subject. You know, master it. But if you're limited in time and energy, then this is your best friend. If you know how to do these things, you'll be fine. So I'll open the floor to question problems that we need to get to before we run out of time, because I've already used up enough of it. Let's see, we've got till 1:45. We have 48 minutes to sufficiently review for the exam on Wednesday. Nobody having specific problems? That being the case, I guess I will just jump in and start talking. Okay. Let's see. Number one is that's a good one. That's a good starting point. Number one. Number one, chapter 3. I think I have it subdivided. Right, chapter 4 begins with 1 again. Right, so I better identify this as chapter 3, number 1. Here we go. So naturally occurring copper exists in 2 isotopic forms. Right, so we know that this copper has a mass number of 63. Right? And this copper has a mass number of 65. So why the difference? Number of neutrons. Right? Can't change the number of protons. If you do, you don't have copper. So this number is different because of neutrons. The atomic mass of copper is 63.55. So we know that the value is this. That's the weighted average of all naturally occurring, of these 2 naturally occurring isotopes. So one of them is going to be heavier than the other, weighted wise, and we can speculate that 63 is probably the major component, right? Because it's closer to 63 than it is to 65. So this is going to be the biggie. The question is, what's the approximate natural abundance of this one? Natural abundance means percent. And if you look at the answers, it's in percent. So the percent of the isotopes, the atoms, will be a certain percentage value for this. How much will this one be? 100 minus that, right? Because they have to add up to 100%. So let's let this one, the abundance of, percent of that one equal an unknown value, x. And for convenience, we're going to use the fractional x, right, rather than the percent. You could use the percent, but I'm going to use the fractional. And then once we find the fractional amount of this one, just times 100, and you get percent. Okay? So this one would be 1 minus x1. Right? Because if we're talking fractional, then the whole has to be this one plus that one. And if you add these two together, you get 1. Right? Okay, so this is x, and this is 1 minus x. So what contribution does this one make to that value? It's that fraction times this value is its contribution. 63x is the contribution to that value from this isotope. And if this one contributes 65 times 1 minus x. And that's equal to 63.55. Okay? Everybody see how I set that up? A certain fraction of this contributes to that mass, and a certain fraction of this contributes to that mass. And since we chose x for that one, why did I choose x for that one? Because once I find out what x is, I've got my answer. If I choose x for this one, then that's 1 minus x. And then I have to do another calculation to find out the answer. So the choice of x is important, that fraction. Once I find out what x is, then all I have to do is multiply by 100. So now that we've got this, then, so I don't have to get my calculator out. Well, I didn't do it in detail, so I didn't get my calculator. Okay, so what is this? Expand that right there. 65 times 1 minus 65x equals that, 63x. So we take this one and this one together, that's minus 2x, right? Right? And then this one, I want to put it on the other side. Right? Before you can solve for x in any expression, you got to have x on one side and everything else on the other side. So this one's going over here as minus 65. Did I lose anybody in that move? I did two things at once. I combined these two, right? And then I put this one over there. So it's plus on this side, minus on that side. And this one stays put. Right? So this is 63.55 and 65 subtracted. That's minus 1.45. Minus 2x. Okay, so what's x? It's that divided by this. Right? Divide both sides by minus 2. That makes this side positive. So, let's see. All right. 72.5. 0, actually, 0.72. So that's the fractional amount. And the percentage amount is just 72.5. Okay? And if you look at the answers, number one rule taking my test is pick the best answer. Right? There's no 72.5 in there. Closest one is 70. Yeah. Did I lose anybody? Okay, that was number one. Let's see.
about, there's a trick question.
Number 3. The average mass of carbon atom is 12.011. That's carbon. Okay? Assuming you were to pick only one carbon unit, that is, one carbon atom. We take one atom. What are the chances that you will find one atom with that mass? Think of how we got that. How did we get this value? It's a weighted average, right? We did carbon 12 and carbon 13. Those are the two major ones, so we just stopped there. And we got this value, right? We did that calculation during the lecture. So what are the chances of finding one atom with that mass? 0%. You will never find one with that mass because it's a weighted average of the isotopes. If there was only one isotope, right, which there never are, but if there were one isotope of an atom and its weight was listed here, then yeah, every atom would be that weight. But no, we're averaging, weighted averaging 2 or more. So you'll never find one that's exactly that value for any of them. Like for, I don't know, copper, 6355. You'll never find one atom with that unit as its mass. Never. Because it's a weighted average. That's the whole point of that question.
Okay. How about, before we dig into any of the other deeper ones, let's do some dimensional analysis. Number 4.
What's the mass of 4 atoms of copper? So you're given 4 atoms of copper. And the question is, what's the mass of those 4 atoms? So you've got to get from atoms to grams. What do we know about copper? Well, we know the atomic number. Is that going to help us? That's just the number of protons. How about this one? That's the mass per mole, right? What is a mole? Mole is the number of atoms. So that's the key. Numbers of atoms, mass per numbers of atoms gets us there. Only we can't go there in one step. First, we have to convert numbers of atoms to moles before we can use that value, because that's grams per mole. Okay. So what do we need to convert atoms to moles? You ever heard of Avogadro? Yeah, he's got a number. That's one mole. So now our atoms cancel, and we got moles. Now we've got relationship of moles to grams. That will get us where we're going. So grams is over here on top. Moles is on top here, so that means we need to cancel it. See that? And anytime you see grams and moles as quotient, grams on top, moles on the bottom, or even moles on top, grams on the bottom, always think molar mass. So the molar mass of copper, in this case, that's what we need, is 6355, rounded off to 2 decimal places. Okay? Right? So that gives us grams. We're there. All we have to do now is crunch numbers. All the thinking's been done. Right?
That's any of the physical sciences.
Do all your thinking first, then do your calculations. Don't try to do calculations with numbers that don't fit the formula. Right? I've seen that done too. But okay, so if we do that, so what's on top? 4 is on top, 63, 55 is on top. So 4 times 63. Okay, that gives you a number. Then you divide it by whatever's on the bottom. 6.022 exponent 23. Divide. And the rest are ones, so divide by 1 doesn't change anything. So what did I get? I got 4. Let's see. Well, 4 atoms is an exact number, right? It doesn't have a limit to the number of significant figures. And these are all exact numbers too, so basically you can pick however many you want. So let's say we stick to 4 significant figures for this one. Well, there's 4 here too, so we're good. So if I do that, 4.221 times 10 to the minus 22 grams. So let's see if we got one that's close to that.
Looks like E, doesn't it?
Okay.
So that's dimensional analysis.
And dimensional analysis will come back to haunt you over and over and over again. Okay. So get comfortable with it. And at the heart of dimensional analysis is conversion factors. That's equal to that. So you can make a ratio out of it. That's equal to that. And you can use those as conversion factors. In fact, each one of these is equal to 1, right? Because that's equal to that, the ratio is 1, right? If that's equal to that, it's got to be 1. So if we needed it flipped like that, to cancel, we could, right? Because it's 1. What's the inverse of 1? 1. Okay, that's number 4. Now, before we run out of time,
Let's move on to, let's see, what would be a good one? Calculating molar mass. Anybody having trouble doing that? Of a compound. Yeah. Let's see, let's pick one that's, here's a complex one, number 11.
this is one where you have, you want the molar mass of a compound that's by name. And you can't take the name and calculate molar mass, right? Because there are no names up here. There are only symbols. So you got to convert the name into a formula. But barium sulfite. Barium sulfite. Okay. So we know where barium comes in, right? It's over here. It's in this family, so that means it has a 2+ charge. And it's in a compound. Right? And sulfite. Do we have any sulfites up here? A polyatomic ion. So you got to look in that list. Should be in here. There it is. Look in that list. Find its sulfite. And then you write it down. And its charge. Okay. Okay. Then you balance the charges. We're fortunate. This one's 2 minus, that one's 2 plus. The simplest ratio is one of these and one of those groups. Remember, polyatomics all behave as a single unit. So you got one of these against one of those, cancels. So our compound is this. Now you can do the molar mass. And all you need is, how many of them are there? Well, there's one barium. 137.33. That's barium. Grams per mole. 1 sulfur. 3207. And 3 oxygens, right? So we need 3 of these. Oxygen 16, rounded off to 2 decimal places.
Right, so 15.99943 is 16.00. Then you add them together. 137.33, 32.07, and 3 times 16 is 48. So that's 217.40 grams per mole. Let's see, is that one of our answers? I gotta flip back to my page. Yep, 217.40 is E. Okay? That's why I hammered nomenclature so hard when we got to it. Because if you don't know how to write a compound, you're dead. But just don't even bother. If you can't write the compound, can't write the formula, then you can't answer the question. Okay. What type of compound is this? Type 1, 2, or 3? Do you remember the types? Type 1, right? It's a metal, non-metal, plus the metal is a fixed charge. So it's a type 1. Right? Type 2 is variable charge, right? So those come from in here and down there. And then type 3 is non-metal, non-metal. Both of them come from over here. Well, plus hydrogen. Okay. That was 11. Let's see. I better get a move on. We're running that time. How about, let's see. Percent by mass. Right? If you're given a formula, you can calculate the percent by mass. Number 26. So if you have this one, NH4, 2 times there. By the way, what is that? Well, you ought to suspect that you've got polyatomics in there. Right? That's a polyatomic. This is a polyatomic. So you get 2 polyatomics. This one is ammonium. And this one is chromate. Now, why didn't I put a Roman numeral in here to say what the charge on ammonium is? Because ammonium is fixed. All polyatomics are fixed charge. And ammonium is the only positive one. It's the only cation in there. So it behaves like a type 1 compound. It's only +1. So all you have to say is ammonium and then chromate. Because chromate is 2 minus, ammonium's 1 plus. That's why you have a 2 here to give you 2 pluses against those 2 minuses. Right? Polyatomics, whenever you need more than one of them, you got to use parentheses. You can't split up a polyatomic. Okay, so that wasn't the question. The question was, what percent nitrogen by mass? So nitrogen percent by mass, and all you have to do is say, how much is contributed by nitrogen? Well, you've got 2 nitrogens, right? 2 times 14.01. Right, that's your nitrogen. Well, what goes in the denominator? The total. What's the total? The total is the molar mass of the compound. The numerator is the molar mass of the component. But you have 2 of them, so you need twice that much. So in this one, you would add this one. Right? Plus 2 times 4 is 8. It was 8 when I was 2 in 2nd grade. I think it's still 8. 1.01 for hydrogen. Right? Then you got chromium. So we go over here to chromium. Rounded off 52.00. We only got 1 of them. Right? So you only need one. And then you got your oxygens here, 4 of them. And go times 100 per percent. So this is your component, and this is the total. So the component is always going to be in the total. Right? If we wanted to know percent hydrogen, well, we just erase that one and put this one up here, duplicate this one up here. Or if we want to know chromium, we just blank that out, take this one and duplicate that one up here. Okay. So it might be quicker to write out the whole like this, in this expression. And then if the question asks for one of these, you just duplicate it up here and bam, then it's just calculate. Crunch numbers. Think first, crunch later. And let's see, that turned out to be 18.4%. Okay. Nitrogen. Okay. Let's see what else is in chapter 3 before we get into chapter 4. Balancing equations, we did that one in this chapter, didn't we? Did we do, let's see, how about 38? Anybody have trouble balancing equations? Using a budgeting method? Let's do one. So 38 starts off with this one. They were nice enough to write the compound out for us. If they hadn't, then this would have been arsenic hydroxide. And in that case, arsenic is -3. -1, -2, -3. Arsenic hydroxide. Actually, it wouldn't be -3. Did we do oxidation states in here? That's chapter 4. We haven't done those yet? Okay, never mind. I don't want to complicate things yet. So this one is a solid. And then we need to leave a space for the coefficient of sulfuric acid, which is aqueous, right? Dissolved in water, that's a solid. And then we get this one, SO4 times, aqueous, plus water. Oh, what type of reaction is this? It just dawned on me. Hydroxyl is a base, hydrogen's an acid. Acid base yields salt plus water. Chemically speaking, that's a salt plus water. So those reactions, acid-base reactions, always give you a salt plus water. Okay, but we need to balance this thing, right? And it's asking us, what's the coefficient for water? So this is the one that answers the question. Now, budget time. Notice that this sulfate is on both sides. And there's no sulfur anywhere else, so we didn't split it up in the process. We can treat sulfate as a single unit for our budget. But this hydroxyl did break up. And actually it combined with hydrogen here to make water. So we're going to have to split it up. Actually, technically, we'd like to get away without it, but that would muddy the waters even more. So let's just split it up. We've got arsenic on this side. We've got 3 oxygens and 3 hydrogens. Actually, we've got 5 hydrogens. 3 here, 2 there. We've got 1 oxygen here that's separate, and this oxygen we're going to keep as a sulfate. So the arsenic sulfate. And then hydrogen, oxygen. So we're good there. Okay, arsenics, we've got one here. We've got, that's not three oxygens. Three oxygens. 5 hydrogens. 2 here and 3 there. And 1 sulfate. Okay. On this side, we've got 2 arsenics. We've got a sulfate, 3 sulfates actually. Right? We've got 2 hydrogens and 1 oxygen. There we go. Did I lose anybody yet? Okay. So if we don't have any standalone elements, right? So we can't hold those in reserve for the end. But acid-base reactions are pretty well behaved. So wherever you start is usually going to end up pretty quick and easy. So if we start with arsenic, we need 2 arsenics on this side, right? That gives us 2 here. But that also gave us 3 times 2 is 6 oxygens. And hydrogens. 6 hydrogens plus 2 is 8 hydrogens. Right? So far, so good? Okay. So how about oxygens on this side? Independent of those. Oxygens here. So if we need 6 oxygens, right, we need a 6 here. Okay. That gives us 12 hydrogens. Is that right? 12 hydrogens. And we need 3 sulfates. Right? We got 1 here, 3 there, so if we put a 3 here, that gives us 3 sulfates. But it also says 6 hydrogens plus 3 times 6 hydrogens is 12. 12 hydrogens. And we're done. Okay? That's the beauty of budgeting like this. You know, you can see at a glance that you're finished. Because they're equal all across. So the answer is 6. Right? The coefficient for water is 6. Now, how could I have done this if I wanted to hold this hydroxyl constant? Well, technically speaking, water is that. So we could have budgeted hydroxyls and hydrogens separate. So we keep these hydrogens for those hydrogens and the hydroxyls for that one. But I figured, that's a little too much for today. But it worked the way we did it. So if you practice this budgeting technique, you can't go wrong. At least at this point, the problems that I'm going to give you are solvable this way. There will come a time when we run into reactions that are very difficult to solve that way, just pure straight budget. And we need alternate methods, but we haven't got there yet. Okay, let's see. Limiting reactants. Limiting reactants. How to tell a limiting reactant. How about that's a complex one. That's good. We can kill 2 birds with 1 stone with this one. 64. I think that's it. Yeah, 64. So we've got this reaction, N2, plus, I'm gonna leave the phases out. We don't need them, not for this problem. And then N2H4. We're told that the percent yield is 82%. Okay? And we're also told that 25.57 grams of nitrogen, 25.57 grams of nitrogen react with 4.45 grams of hydrogen, 4.45 grams of hydrogen. And the question is, what's the actual mass of hydrazine? Oops. How many grams of hydrazine do we actually get from the reaction with that percent yield? Okay? So, whenever you see two reactants with absolute amounts, think one of them is limited. One of them is going to run out first. So you got to find out which one. Because the one that runs out first determines intermediate answer. Right? Why do I say intermediate? Because if you make the calculation with the limiting reactant, you get the stoichiometric amount, 100% yield. Then you have to apply that to it. Okay, so it's a two-step problem in this case. So how do we find out how many grams of that are produced? Can't go anywhere in an equation with mass, right? Just remember that rule. Has to be moles. So first thing we have to do is convert that to moles. And how do we do that? The molar mass. Grams on the bottom, moles on the top here. Moles on the top. These grams cancel. That's why I put grams on the bottom and moles here. So for every mole, what's nitrogen? Notice there are two of them. Right. So 1401 times 2 is 28.02, isn't it? That's the first, that's the potential for the first mistake, is not taking that into account. So that gives us what? 25.57 and 28.02 gives us 0.9125 moles of nitrogen. Okay? Now we do the same thing for hydrogen, 4.45 grams. But we need a different molar mass, right? We need two hydrogens in that unit. 1.01 times 2. 2.02. Right? We take this one, 4.45, and divide by 2.02. We get 2.20. 297. Okay. So, how do we change this? We have to find out. Okay, here's the next step. To find out which one runs out first, you just say, what's the one that produces the least amount of product? That's the one that runs out. So you convert this to that, and you convert this to that, to find out which one is the least. So to do that, what do we need? So we got N2 here, moles of N2, and N2H4 here, because you want to cancel these. So the coefficients tell you your conversion factor, 1 and 1, 0.916 moles of hydrogen. If we use up all of this. If we use up all of this, it's a different conversion factor. We need to cancel hydrogens and leave us with hydrogen. We've got 1 here, 2 there, we take half of that, 2.20297 is 1.1015. 1.1015 moles. See, so which one is limiting? This is. It produces the least amount. Right? Now that we know the one that runs out first, this is the most you can get. Can't get any more. Right? Because when it runs out, the reaction's over. You won't get that, you'll get this. Right? So this is the amount of that you produce. Okay? So we got that many moles, but the question is not moles, the question is grams. So how do you get grams from moles? Mole grams. So what's the molar mass of N2H4? Let's see. It's 2 times 14.01 for nitrogen and 4 times 1.01 for hydrogen. 2802 and 404. I got 3206. That sound right? So it's 32.06 grams there. So 3206 times 91256. Let's see. Is 29.26. Grams of hydrazine. So that's your answer. Let's see if that's one of them. 64. Okay, the nearest one is he's not right. Why? I mean, the answer's there. That answer is there, but it's the wrong answer. Right? Remember why? I didn't do percent U. That's what you get if it's 100%. Right? So we need 29.26 times 0.82. Okay. Let's see, rounded off 24.0 grams. Let's see if that one's there. 64. Yep, that's B, 24 grams. Okay. We're going to round it. We'll get to chapter 4. Let's see if there's anything here that, yeah, we covered all those bases. Well, empirical formula. Right. If you have a room here. So if we look at 73, let's take maybe C. Right? So if that's the molecule, right, you see the carbons, oxygens, and hydrogens in their circles. If that's the molecule, then what's the molecular formula for C? Well, let's see. Let's count the carbons. 1, 2, 3, 4, 5, 6. Okay? Let's count the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. And oxygens. 1, 2, 3, 4, 5, 6. Okay? That's the molecular formula. But the question's asking for the empirical formula. So what is the empirical formula? The simplest whole number ratio. Can you divide that through by anything that will simplify it?
Okay? If you divide by 3, you get 2, 4, and 2. How about, can you divide that one through by anything? Right, 1, 2, 1. So the formula, the empirical formula is CH2O. Okay? And you can do that same thing with any of those others and get the right answer. Now, what we didn't get to, in addition to chapter 4, was calculating the molecular formula based on raw data. Do we need to do that? Okay. 74, let's do that. The hormone epinephrine is released in the human body, blah, blah, blah. That's the blue smoke. The meat of the problem is, and actually, if you read from the bottom up, determine the empirical formula. But we would need to know the empirical formula for this compound. And with the data that you're given, percentage composition, 59% carbon, carbon, 7.15% hydrogen, 26.2% oxygen, and 7.65% nitrogen. What's the next step? What are we aiming for? We're aiming for the ratio of carbon to hydrogen to oxygen to nitrogen. All right, so little c, little h, little o, little e. These ratios, those ratios are numbers of atoms in the molecule. Right? These are not numbers. I mean, definitely not numbers. Those are dimensionless. Parts per 100. Even if you find the mass, that's still not the right ratio. Right? This is not mass ratio. This is numbers. So you've got to, in order to get mass, you've got to assume a sample size. Right? And if it's parts per 100, that's like grams per 100 grams, right? So if we assume 100 grams sample, simple. Now we got 59 grams of carbon. We can deal with that. 7.15 grams of hydrogen, 26.2 grams of oxygen, 7.65 grams of nitrogen. Now we just need Henry Ford. Start our assembly line. Cancel grams. Leave us with moles. Okay? So what's the magic number? Well, carbon is 12.01 molar mass per carbon. Hydrogen is 1.01. Oxygen is 16 grams per mole. Nitrogen is 14.01 grams per mole. Okay. So now we can crunch some numbers. We've done some of our thinking. We can crunch these numbers. So this one is 4.913 moles in that size sample. 7.15, oops, back up. 1.01, this is 7079. Okay. 26.2 divided by 16 is 1.638, and 7.65, 14.01 divided into that is 0.5460. Okay,
So those are ratios, molar ratios within the compound, but they're not the simplest whole number ratios. So we've got it, and these ratios are established. Right? 4.9 to 707 to 1.6 to 0.5. They're fixed. So if we do something to any of them, multiply, divide, well, can't subtract, but if we multiply or divide by any of these, we don't change the ratio. Right? The ratio is fixed, but we want to convert them to whole numbers. So the simplest way to convert them to whole numbers is divide by the smallest one. Let me see if I'm not telling you wrong. I'm pretty sure. Pretty sure that's it. Yeah. I did a little different in the work problems, but we're going to get to the same location. Divide by the smallest one, right? It's like see the kicking in. We'll divide each one by that number. Of course, this one's easy. Then we want 1.638, 5.546. This one's 3, exactly 3. 7.079 divided by 0.546. This one's 12.965 rounded off to 13. Very close to 13. And 4.913. This one's very close to 9. 8.998. Right? So we didn't have to do any more. That's it. We got whole numbers, and you can't simplify them any further. That's the test. Can we divide these through by a number and simplify them further? No. That's prime, that's prime, that's prime. You're not going to find a divisor that's common to any of those. Right? Remember prime numbers? You can only divide by 1 in the number. Right? So they have nothing in common. That's as simple as you can get it. So if we write the formula, C9, H is 13, O is 3, and N is 1. So that's your empirical formula for epinephrine. Okay? Now, we're out of time. We haven't got to chapter 4 yet. Let's see. Yeah, 1:45. We're past time. So, if you got to go somewhere, fine. If you don't, I'll pick out a few more and talk about them. Record it. Right. And anybody on Zoom, if you want to hang around, fine. If you have to go, I'll keep recording so that we can get some type of review out of chapter 4. I'll pick out the main. Unless you want to tell me in advance, is there something in 4 that's bothering you? Then I'll be sure and get to it. Otherwise, I'll just look at the review document and I'll pick out topics that have been covered in there and be sure that I cover each one as a review. Okay? And we'll see you on Wednesday for an exam followed by a lab. Yeah, followed by a lab. This is chapter 4. There. And then let's look at some problems in number 4. Let's see what we got going for us. Yes, I'll assign it. That's great. Go ahead and close. All right, chapter 4. Well, let's just start with the basics. How about number 1? An unknown substance dissolves readily in water. Okay, so our substance is soluble. It goes into water readily. But benzene no, it does not dissolve in benzene. And additional information is given is benzene is a non-polar solvent. Right? So our substance is soluble in water, and water is a polar substance, but it's not soluble in a non-polar substance. What does that tell you about X, our substance? It tells you that X is probably polar, because like dissolves like. So let's see what the question is. Molecules of what type are present in the substance? All right. Actually, the unknown substance, it doesn't tell us that it's pure. It could be a mixture. But everything in the substance goes into solution. So whatever is in the substance has to be polar. It cannot be nonpolar. If it's nonpolar, it would have dissolved in benzene, or at least part of it would have been. If the whole thing dissolves in water but not in benzene, then it's got to be polar, and that's the end of it. Okay. So that was, the answer to that was B. Okay, let's see. And 2 is a definition. When a substance interacts with water, which tends to cause whatever the salt is to fall apart in water, it's called hydration. That's just the water molecules are attacking the ionic crystal and pulling off cations and anions. Let's see. Number 4, all of the following are weak acids except. All right, so we have these choices. HCNO, HBr, HF, HNO2, and HCN. Just for fun, let's name these things. Well, this one's going to be difficult to name. So, I don't think that one's in your chart. That's definitely a polyatomic. Let's see, what is it? I'll get there eventually. There you go. CNO. I'm looking for that combination. No, not one of them. Okay, so that's kind of a trick question. What we're saying is they're all weak except one of them is a strong acid. This one is what? There's no oxygen, so it's hydro. Cyanic acid. Nitrite. Ites become us's. So this is nitrous acid. Right? Because there's an oxygen. This is a hydrofluoric acid. This is hydrobromic. And that's unknown. All right, so that's not a good question, really. Unless you know that this one is weak. This one is weak, this one is weak. So the real question is, which one of those is strong? If you simply go by electronegativity, you would say, okay, they get stronger. Actually, they get stronger this way. So hydrofluoric, hydrobromic, hydroiodic are all three strong acids. And HF is a weak acid. So this is the only strong acid in there. All right, let's see if we've got some other choices here. Where am I? I need to be, here it is. Okay. Let's try calculation of molarity, 9. So what's the definition of molarity? Moles per unit volume. And the volume has to be in liters. Right? So with number 9, we've got 16.4 grams of hydrogen fluoride. And it's going to be dissolved in water to give us a final volume of 2 times 10 to the second milliliters. Right? So we got two problems here. This has to be converted to moles, and this has to be converted to liters. Right? So let's take the easy one first. So if we've got milliliters and we're going to liters, you need to, this is going up, increasing, right, in size, milliliters to liters. That means this one has to go down. So we're going to go 10 to the minus 3 against that, which would be 2 times 10 to the minus 1 liters. Another way to look at it, 2.0 times 100, or move 2 places, 1, 2. So we would have 200 milliliters. Now we can move 2 places, 3 places, 1, 2, 3, 0.20 liters. Okay, either way works. This one we have to convert to moles. So we need molar mass for HF. So 1.01 for this one. And fluorine is 19.00. So that looks like 2001. Right? So 20.01 divided into 16.4 gives us the number of moles. And that's equal to 0.8196 moles. Now we can do the calculation. We've got liters, we've got moles, moles per liters. So that's 4.098 molar, or the best answer that satisfies that one, which would be D, 4.1. Okay? Simple calculation. You just have to know the formula you're working from and the information you're given. If it's not in the right form, you got to convert it to the right form. So this had to be made moles and this had to be made liters. Then you can do your calculation. Okay, that was number 9. Let's see. What if we do number 14? working with the same formula. But now the question is, what mass of calcium chloride? So the grams of calcium chloride required to produce 3.950 liters of 1.49 molar solution. Right? So this we're given here. This we're given here. So we need to go for that one. Right? So if we substitute these values in here, or let's solve it for moles first. Moles equals molarity times volume. Right? Let's move this one over here. Then we can substitute in here molarity 1.49 times 3.950 liters gives us the number of moles of calcium chloride required. Which is 5.886 moles of calcium chloride. But the question is for grams. So when you've got moles and grams in the same sentence, make molar mass. Calcium is 40.08, 40.08, and then 2 times chlorine, 35.45. Right. So we add those together, and 2 there, 35.45. So I get 110.98. So to convert this to grams, moles on the bottom, grams on the top, 110.98. And we get 65, let's see, what are we limited to? 3 significant figures. 65.3 grams. Let's see if that's in here. Number 14. Oops. My mistake. 653. I didn't move my decimal place far enough. 653 grams of calcium chloride dissolved in water to make 3.950 liters will give you this concentration. So we use the same formula, we just solved for a different part of it. Okay. Have anybody? Oh, still got somebody hanging on. Okay. That's all right. Let's see. Let's try something a little different. About 17. This is both a calculate molarity plus a dilution problem. So this has got 2 steps in it. Our initial solution is composed of 74.28 grams of barium hydroxide in 2.450 liters. Then we're going to take so many milliliters of that and dissolve it in 1 liter to make a 0.1. So our target is 0.1 molar barium hydroxide. Okay. So first we need to find out what's the molar concentration of this one. Okay. So we need to convert that mass into moles. and we need molar mass to do it. So barium is 137.33. 137.33 for barium. 2 oxygens, 32, right? 2 times 16. 2 hydrogens, 2.02. Add those together. Uh, 171.35. 171.35. So that goes right here. Right, we got to cancel grams. Divide that into 74.28. And I get 0.4335 moles. And we're going to dissolve that in this many liters. So the molarity of our concentrated solution is equal to this many moles of barium hydroxide in 2.450 liters. And I get 0.1769 molar. Okay? So, next step. We're going to do a dilution. So we have the concentrated molarity and the volume of the concentrate, then the molarity of the dilute and the volume of the dilute. So this is the diluted molarity, 0.100 molar. This is the concentrated, 0.1769 molar. I did that right. Yeah, I think I did that right. Now, what's the question? The question is, how many milliliters of this solution must be diluted with water in order to make 1 liter of that solution, right? So now that we've got our terms divvied up properly, we can use the formula. Molarity concentrated, volume concentrated equals molarity dilute, volume dilute. Right, so we just plug in the numbers now because we've done all our thinking in advance. This is the unknown. This is the diluted molarity, and this is the volume. But notice the question is, how many milliliters of that, right? So if we're going to make 1 liter of this, how many milliliters of that is there? 1,000. Right? The reason I did that is because if you solve it with milliliters over here, then your answer comes out in milliliters. Otherwise, your answer will come out in liters, and you'll have to convert. So 0.1769, okay. Then we're going to take this and divide it into 0.1 times 1,000. And I get 5565.2 milliliters. So let's see if that's one of the choices. 17, yep, A. So the answer, this is A answer. 565 milliliters. Okay. All right. Let's see. Let's do a stoichiometry problem in solutions. Let's see, 24. So here's our reaction. Aqueous solution. What is this? If that's -1, two of them, this has to be 2 plus. This is iron 2 chloride. Plus 3 of these, oxygen gas, yield Fe2O3, solid. That's rust, iron 3 oxide. There, that's our controlling reaction. So the question is, what volume of 0.76 molar solution of this? So we got 0.760 molar solution of that. And we want to know the volume of that solution that's required to react completely with 6.36 times 10 to the 21 and 10 to the 21 molecules. Of oxygen. Complete react. So we want the stoichiometric amount of this. So that looks like a bear of a problem, but it's really not. But what do we need to make this comparison? We need moles, right? We can't get moles here because we don't know the volume. But we can get moles here, can't we? Just convert that to moles. And then we can move over there. So how do we get moles here? This is in the numerator. Don't forget that. The molecules goes down here, and moles goes up here. 1 mole, 6.022 times 10 to the 23rd molecule. Right? So that'll tell us how many moles of oxygen we actually have to react with the iron 2 chloride. 6.36, 21, and then divide that by 6.0223. So I get 1.056 times 10 to the minus 2 moles of oxygen. So how many moles of iron 2 chloride do we need? Well, once you've got moles, you can go anywhere. You just need conversion factors. And conversion factors for this step always come from the coefficients. So we're going to cancel oxygen and make iron 2 chloride. Coefficient of iron 2 chloride is 4. Coefficient of oxygen is 3. So we need 4 times that divided by 3. And I get 1.408 times 10 to the minus 2 moles of iron 2 chloride. So now we know how many moles we need here. And remember the definition, molarity equals moles per volume. Let's see, the volume asked for is in milliliters. So in this case, we don't have a ratio. So we've got to calculate the volume in terms of liters and convert to milliliters. It's unavoidable. So if we're going to solve for this one, V equals N divided by molarity, right? You just swap these two. Okay. So the number of moles is 1.408 times 10 to the minus 2 moles of iron 2 chloride derived from 0.760 molar, right? So I get 1.853 times 10 to the minus 2 liters. And you can either convert that to standard notation and move decimals, or we could use dimensional analysis, right? 10 to the third milliliters is 1 liter. Liters cancel. So 10 to the third times 10 to the minus 2, just add the exponents, which means 10 to the first, 1.853, which is 18.5. Yeah, 3 significant figures. So this is in liters, this is in milliliters, and let's see if that's one of the answers. 24. D. That makes D the answer for 24. Okay? All right, 24, let's see if I can find something that's different. Okay, now we've got a sequence of reactions. I think I've already done that one in class. Identifying reactions. Let's go to 27. 27 has these reactions to choose from. Oops, I'm all by myself now. Okay, plus bromine yields KBr. This one is silver nitrate solution plus sodium chloride solution yields silver chloride solid plus sodium nitrate solution. And the last one, HCl plus KOH yields water plus KCl. Okay. Now, one thing you can do is look at the possible answers. And that's okay to see which one matches. That's only if you know what you're looking at. Right? So, let's take from the bottom up. Acid, right? Proton, hydroxyl. Acid, base. That's an acid-base reaction. Solution plus solution of two compounds yields a solid plus solution. That's precipitation. An element plus an element yields a compound. This is, let me see what terminology they're using. Okay. This is a synthesis, but that's not one of your choices. So what type of synthesis is it? Well, if this is a element, that's an element, and this is a compound, what's that trick I showed you? If you've got an element on one side and a compound on the other for that element, you have a redox reaction or an oxidation reduction reaction. So which ones satisfy those conditions in 27? Precipitation reactions. No, they're not all that. Redox, precipitation, and acid-base, respectively. Redox, precipitation, acid-base. So it's B. You don't even have to go any further. So it helps to know what type of reactions you have, and then go look at the choices. But occasionally you have to look at the choices and see, in this case, I would have said synthesis first, but it's not a choice. So redox is the choice. And that's a case where this is one type, actually one reaction, two different types. So let's look at some of these others and see if I can find one that's throwing you a curve. Okay, 28. 28 is precipitation first and a precipitation second. Both of them are precipitations, 28. 29. That one says all of the following reactions, blah, 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 can be classified as what? Well, if you look at the first one, you've got two elements making a compound. Second one, you've got a compound making two elements. Those are both oxidation reduction. So the question is the third one oxidation reduction? Well, the third one for our 29, the third one is methane plus oxygen yield CO2 plus water. Okay? So we see that here's an element, and over here, it's in a compound. So that one is also redox. But for argument's sake, what else is it? I mean, the answer to A then would be A. All three of those were redox reactions. But the first two, the first one is a synthesis. The second one is a decomposition. But they're also redox reactions. That's more to the point of the question. This is a redox, but what else is it? I mean, it's not answer the question, but it's also a combustion. Right, because of this. And all combustion reactions are redox reactions. Every time, always, forever. So let me see if there's any other in here that might give us a twist. Ooh, 30 seems a bit 30 would spin your head around. You have exposed electrodes of a light bulb in a solution of sulfuric acid. So we got this solution right here. And in that solution, we got an electrode here, an electrode here. They go to a battery. And they also go to a light bulb. So we do that. So the light bulb is on. And why is the light bulb on? Because sulfuric acid dissociates into ions. And that makes the current pass through the solution. If you got mobile ions, you're good to go. But we're going to change the conditions. You add a dilute solution and the bulb grows dim. So we got a bright bulb first, and then when we add something to it, we don't know what it is yet, the bulb gets dimmer. So what are we doing? When we add something to this solution, we are tying up the ions, right? So I'm going to hazard a guess. When we add something to that solution, it's going to precipitate out some of the sulfate and or the hydrogen. Could be both. And reduce the number of ions in here. That's why the bulb gets dimmer. So our choices. What are our choices? First choice, barium
hydroxide. Second choice, sodium nitrate. Third choice, potassium sulfate. Fourth choice, copper nitrate. And E, none of these. So that just means we added something to it and it's not in the list. Do any of these serve as a remover of ions? So let's see, what would happen if we reacted this one? And these are all aqueous solutions, right? A dilute solution, you add a dilute solution of each one of these. So they're all aqueous solutions. Okay, so what happens with each one of these reactions? H2SO4, aqueous solution. Notice that's a base and this is an acid, right? So what do you get with an acid and a base? You get barium sulfate, right? And water. So barium combines with the sulfate and you get actually two waters to balance it. So does this remove ions from the solution? Well, if barium sulfate is soluble, no, it doesn't, right? So we need to find out, is barium sulfate soluble or does it precipitate out, removing ions from the solution? Right? Just look at the back, this thing right here. Right? So let's look at barium across the top. There it is. And then follow it down to sulfate. Uh-oh. Makes a solid. That one works. Now, test-taking technique. Since we don't have two of the above or three of the above or those types of choices, you found the answer on the first try. Right? If we add this one, H2SO4, what do we get? Well, if we swap ions, sodium sulfate, this is 2, and H2NO3, well, that doesn't work, HNO3. That's not balanced, but it shows us that sodium sulfate is soluble. All you have to do is look it up, right? And nitric acid is soluble. So you haven't removed any ions at all. How about this one? H2SO4 and KSO4. That's K2. K2. So what's the difference? There's no difference. The products are the same as the reactants, so you didn't have a reaction. There's no reaction here at all. You got the same on this side as you do on that side. How did I get that? I swapped K's for hydrogens, right? It's a double displacement reaction. So hydrogen goes over here, K goes over here, and you get the same compound you started with. How about this one? Do the same thing. Copper swaps with hydrogen, so we have copper sulfate and HNO3. Not balanced, but this is aqueous. How about copper sulfate? Well, let's just look. Let's see. Copper. There it is, copper 2. And sulfate is soluble. Right? So none of these will change the light bulb. Right? You've got the same ions here. Actually, since this is soluble and both are soluble, you're adding, you're adding ions here. You're adding ions here, you're adding here, you're adding here, you're removing here. So the bulb ought to get brighter here with these three. And it gets dimmer with this one only because we precipitated out the ions. We reduced the number of ions, so the bulb gets dimmer.
And the answer is A. Okay? So that problem could have spun some heads around. I mean, if you try to solve it all in your head, then you're going to have trouble. You got to write it out and reason it out each step to see which one satisfies the conditions of the problem. If you don't do that, you're asking for trouble. And you're going to get it. Okay, so let's see if I've got some others in here that we can talk about. 32 just asks you which of these salts is insoluble in water. And you just have to look them up in your chart. Look up the cation across the top, the anion across the side, find where they meet, and look for the grade cell. If you don't find one, then it's soluble. Let's see. Okay. 36. 36, I think. Am I jumping the gun with 36? Yeah. 36 is the bad question for this chapter, or for these two chapters. Cross out 36. Don't bother with it. We could do it, but it really you're treading on thin ice when you try to solve this one with what we know now. So let's just throw 36 out. It won't appear on the exam. And even if it did, call my attention to it, and I'll throw it out. I'll just give you credit for it. So let's move on. Let's see. How about 38, 39, and 40? We didn't spend a lot of time on these at the end of the lecture. So let's 38, 39, 40. They're all related. Aqueous solutions of barium chloride and silver nitrate are mixed to form silver chloride and barium nitrate. So we actually tell you the reactants and the products. That's nice. We don't give you the formulas, right? You got to figure that out yourself. So the first question is, the balanced molecular equation contains which one of the following terms? In that case, you have to balance the molecular equation. So we need barium chloride first. Barium chloride solution. So we need to write that correctly. What's the charge on barium? Right? This is a metal, this is a non-metal. Where's barium? Barium is in the second column. That makes it a 2+ ion. So that means we need 2 chlorine. Right? Because chlorine's -1 against barium's 2+. We need to balance the charge. Then silver nitrate is added together with that. Okay. Silver is one of those, well, you can't see my chart, but silver is one of the elements in the transition elements that has a fixed charge. So it's okay to say silver nitrate. You don't have to say silver 1 nitrate unless you want to. But silver nitrate is 1+ charge, 1- charge. That's the formula. Then it tells you what the products are. We can do the products ourselves. Just swap silver and barium. So silver goes with chlorine, and barium goes with nitrate. The question is it soluble? Well, barium nitrate, look up barium nitrate, all nitrates are soluble. You can look it up, or you can go by the rules. Silver chloride is insoluble. This is a -1, +1, that's good. This is a +2, that's a -1, so we need 2 of those. If you don't get this right, the proper molecular formula, then the rest of them are moot. You can't do them. You've got to get these right. So now we can balance the equation. We can probably balance this without doing the budget thing. So let's look at, we got 1 nitrate here and 2 there. Well, let's put a 2 here. All right, 2 nitrates, 2 nitrates. Now we got 2 silvers. All right, so we need 2 silvers. That gives us 2 chlorides. We got 2 chlorides. Is that right? Barium, 1 barium, 2 chlorides, right? 2 times 1. 2 silvers, 2 silvers, 2 nitrates, 2 nitrates. We're balanced. That's the complete molecular equation. Right, so the question is, which one of the following terms? AgClS? No, it's 2 AgCl. Right? B is 2 AgCl. Right? So this is correct if we say B. You can go through the rest of them, but that's the right answer. Now, 39, the balanced complete ionic equation contains which of the following? Now that the molecular equation is balanced, we can write the complete ionic equation. Anytime you have aqueous, you can bust them up into their individual ions in solution. Right? So we have 1 barium in solution. We have 2 chlorides in solution. We have 2 silvers in solution. And we have 2 nitrates, coefficient times everything inside. 2 nitrates in solution. Now, what does that yield? It yields 2 silver chlorides. This is a solid. You can't break it up. So it stays the same. But this one is in solution. So we have 1 barium in solution plus 2 nitrates, right? This is polyatomic, so this subscript means there are 2 of them. There. That's the complete ionic equation, and now we look at our answers and see which one fit. Well, A is 2 barium 2 plus. No, there's only 1 of them. B, 1 chloride. No, there are 2 chlorides. That won't work. C, 2 silver ions. Yes, 2 silver ions here, none there, but there's 1 right there. So that one satisfies. You could go through the rest of them, but that's the answer. Now, the net ionic equation contains which of the following terms? How do we do the net equation? You find your spectators and cancel them. So what does not change on either side? We got barium here. We got the same number of bariums there. Right? We got a chloride here, but the chloride is in a compound over there. Can't touch it. Silver, it's in a compound on this side. Can't touch it. Nitrate, we got 2 nitrates here, 2 nitrates over there. Now, what's left over? That's your net ionic equation. So this is the molecular. This is the complete ionic. This is the net ion. So now that we've canceled out our spectators, whatever's left. Okay, we have 2 chlorides plus 2 silver yields 2 silver chloride. Now, what do we say about these equations. If we can, we simplify the whole number coefficients, right? 2, 2, and 2. Divide the whole thing through by 2, and you get this plus this yields this. This is the net ionic equation. So then we look at 40 and say the net ionic equation contains which of the following? Well, let's see. AG plus AQ. There it is. B, barium. Barium's nothing there. Nitrate's not there. Hydrogen wasn't there to begin with. And silver chloride aqueous is not there because it's a solid. This is the answer, and it's A. Okay? So, one lesson on writing balanced equations, complete ionic, net ionic, in 3 problems, and we're done with that topic. There are other problems in here where you use that. For instance, toward the back, I think there's some balancing equations in the back. Right. Let's see if there are any others in here that need our attention. Let's see. That looks like a trick question. I'm going to look at that one just a second. Just a second. Let's make room. Let's make room for number 47. Let's look at the question, 47. Calculate the concentration of sodium plus, which is a sodium ion, after the 2 solutions are mixed together. So we're looking for the concentration of sodium in the solution after mixing. All right. So what are we given? Well, we're given, you have a solution of sodium chromate, right, aqueous, and we have 88.6 milliliters of 2.50 molar solution. And then we're going to react that with silver nitrate. Oops, I don't need that. +1, -1. Okay. Yields what? Oh, excuse me. 125 milliliters of 2.5 molar. Okay. Now the question is, what's the concentration of sodium in the solution after the reaction? So let's see what the reaction is. It's a double replacement reaction. You swap the silver with the sodium, right? So silver combines with chromate, right? Silver is a +1, chromate's a 2-, so that means 2. And you look it up in your chart, right? There's silver, follow it down to chromate. Yep, sure enough, it precipitates, right? So you're going to precipitate the silver with the chromate, and what's left over is sodium and nitrate. Right? So sodium nitrate, and you look it up, all alkali metals are soluble, all nitrates are soluble. It's got to be soluble. So what does that mean? That means that all the sodium that you put in here ends up over here. It's a spectator. So all we have to do is calculate the concentration of sodium. Because none of it was consumed, there's going to be that much sodium in solution. We just need to know how much sodium did we start with, right? So let me show you a trick. If this is our calculation, our formula, controlling formula, and we want to know how many moles it is, M times V, if we know molarity and volume in liters, then we get moles, right? But if you know volume in milliliters, multiply them together, you get millimoles, right? That's a new unit. Millimoles just means 1,000th of a mole. If you multiply milliliters times molarity, you get millimoles. The reason I say that is, this way, I don't have to change to liters. So if we multiply these two together, (88.6) and 2.5, we get 2.215 times 10 to the second millimoles. Notice also that if you divide moles by, if you divide millimoles by milliliters, you get molarity. Right? So as long as you've got milli together, you get molarity. If you got moles liters together, you get molarity. Here. If you got millimoles divided by milliliters, you get molarity. Right? So we got millimoles here to start with. Now, how do we calculate the concentration over here of sodium? Well, we know that we started off with this many millimoles of that compound. How many millimoles of sodium does that mean? The ratio is 2 sodiums for every compound. So we actually have 2 times that. Millimoles of sodium. This is millimoles of compound. Okay? That's a crucial step. And you wouldn't know that unless you looked at the formula. This is molarity of the formula. Okay? So this is the millimoles of the compound. This is the millimoles of sodium. Now we have millimoles. It's the same on both sides. We didn't do anything with them. They're still in solution. All right? So what do we need? We need milliliters of solution. Right? Millimoles divided by milliliters is molarity. So we got to calculate how many milliliters do we have in the mixture. Well, it's just this one plus that one. Right, so 88.6 and 125 is 2.136 times 10 to the second milliliters. So if we divide this into that, we'll get our molarity. 2.07 molar sodium ions. Now, let's see if that's in the answers. Or am I just all wet? Nope, that's right. This is C for number 47. Okay? Let's see what else we can find before I run out of energy. If I stop talking and sit down, it's all over. I won't be able to get back up. Let me see. Oxidation states. Right? We haven't talked about that yet. Calculating oxidation states. So let's do 52. Nitrogen is notorious for having lots of different oxidation states in a reaction. Remember what an oxidation state is? It's a bookkeeping technique. It doesn't mean charge. It means this is how we track electrons in a reaction, right? We do it by something that looks like a charge but doesn't have to be a charge. We call it oxidation state. For that reason, we don't call it a charge. Okay, so for this one, we have down to E. C, D, E. Okay, this one, this one, this one, that one, and this one. Okay, how do we do oxidation states? Well, you need rules. All these compounds are neutral. That means oxidation states for all of the elements within there must add to 0. Okay? And what else? We have some established accepted values that allow us to compute the others. Right? So oxygen is always 2 minus. Unless, of course, it's a peroxide, and there are no peroxides here, so we don't have to worry about it. 2 minus for oxygen, and hydrogens are +1. Right? So, if we have to be neutral, then the nitrogen, 1 nitrogen plus 1 for hydrogen, and how many minuses for oxygen? Well, minus 2 times 3. That's 6 minuses, and 1 plus means minus 5. For that group, that means nitrogen has to be +5 to balance it. There's another way to do it. Right? So we've got a +1, -2. I mean, this is a +1. This is 3 times a 2 minus, which is -6. Right? So those together are -5. And this one has to balance that -5. Okay? So for this one, nitrogen is +5. Okay? So let's do this one. Oxygen is 2 minuses, so that means 4 minus for oxygen. And there's only 1 nitrogen, so that nitrogen has to be a +4 or a 4 plus to balance that. Okay? This one's 2 minus for oxygen, but there's only 1 of them. So this nitrogen, these 2 nitrogens balance that 2 minus, so the total is 2 plus, but each one is a single plus. This one, chlorine, is 1 minus. Hydrogen is 1 plus, so that's 4 pluses. Right? So 4 minus 1 is +3. That means this nitrogen has to be 3 minus. That one, that one. Now for the last one. This is a +1 sodium, 2 minus for the oxygen, which means 4 minus total. So 4 minus and 1 plus is 3 minus. That means this one has to be 3 plus. Okay. So the question was, which one has a +4 charge? Oxidation state, excuse me. Oxidation state. That's 3 plus, 3 minus, 1 plus, 4 plus. Here we go. It's B. You need to know how to calculate oxidation states. So for something like 54, where we have ClO minus, what's the oxidation state of chlorine? Well, in this case, you have a polyatomic ion, which has a charge. So the sum of the oxidation states must equal the charge, right? So if oxygen is 2 minus, and we have to reserve one of them for that minus, that means we only have to balance that 1 minus. So this is 1 plus for chlorine. That makes 54. Answer is B. Let's see. How about, I want to find one that I can make multiple statements about. Okay, let's do 56. Won't take long. In this reaction, oops, small. Okay, in that reaction, the question is, which species is oxidized? So remember what oil rig oxidation is loss, right? Oh, do you have a class coming in here? What time?
3 o'clock.
Okay, I'll get out.
That's all right. That's okay.
I'm just finishing up a lecture. You know, it's just, that's all right.
No, are you live?
No, no, it's recorded.
Oh, okay. So let me ask you, I'm glad you're here because I want to record some lectures too because this is my MC people.
Yeah.
And
Okay, guys. We're up and up against another class coming in, so that's the end of the review. Just use the review document and the worked problems that go with it, and you'll be fine for the exam. See you on Wednesday.